Thank you so much. My name's Tom Kornack. I'm going to talk about the work that many people have contributed to at Twinleaf. It's Mark Limes, Jill Foley, myself, Nancy Ford, Michelle Rizzo, and Alan Nelson. And it's crucial in this particular sensor that I'm going to talk about. It's crucial to appreciate how much effort it is to actually build it, and especially the last three people here put an enormous amount of effort to make it happen. Twinleaf is a small company. We are 10 people. We're 12 years old. We focus on magnetometer R&D, and so we try to do as much of the fabrication as possible in-house. So we try to make our own cells and everything really, almost except for the laser, and that's actually something that sort of is changing with this work. Our work is based on patents that we've applied for ourselves and licensed from Princeton University. And we've got a nice new facility in Plainsboro, New Jersey, which is one town over from Princeton. I hope you'll come visit us. New Jersey is a beautiful place. Here's sort of the things we do as a company commercially. And of course, the things that we do for research are much more broader. But we make a variety of magnetometers, total field magnetometers, and I'm adding this new pulse magnetometer. It's not quite a stable product yet, but it will be. Surf magnetometers, and I don't know why this is distorted here, but we make shields. They don't look like that. It got dropped, yeah. It's a problem with shipping. We make our own cells, we make current supplies and things that support these things. And complete systems like this GNOME station here. So today I'm going to talk about a pulse magnetometer and what we could try to use it for especially for measuring the heart. And so a pulse magnetometer is one where you pump in sort of very quickly with an intense pulsed laser, and you polarize your atoms, and then you watch those atoms as they precess with a probe laser. And they just sort of spin down. It's a free induction decay measurement. And so the raw data looks something like this. So you pump, and you pump in a microsecond or a fraction of a microsecond, then you watch the precession. So this is a very simple system. And so, why would you do this? The reason you might do this is that with pumping in a pulsed way, you can just blast the atoms and you can get them to the absolute maximum polarization state. And that's sort of maximizing the signal you can get out of your atoms that you happen to have. It also sort of resets the magnetometer. There's no time history, no hysteresis. So that makes for nice flat bandwidth. Every pulse is independent. And when you turn off your pump laser, there's no pump light shift. So that's a nice feature, and that's something that really matters at this level. And frequency measurement, as Mike Morales has said, it's the only way you get to such high precision and to have such high dynamic range. So by comparison, if you were trying to track a resonance, you have all sorts of issues that people may be aware of. I don't need to go through in detail. But this is, it's not necessarily flat bandwidth. You don't have to, our system has flat bandwidth. There's no frequency feedback or PLL necessarily. It's independent of signal amplitude. You don't have to balance your cells, all the things that Mike has already talked about. So the simplest pulse magnetometer looks like this. You have a pump laser that's circularly polarized. It goes into the cell. And you have a linearly polarized probe laser. You bounce through the cell, and you read it out with a balanced polarimeter. So this is sort of a simple pulse magnetometer that we're making and that we can sell sort of in prototype quantities. And it has sensitivities under 200 femtotesla per root hertz and bandwidth of a kilohertz, or I should say a sample rate of a kilohertz. And it operates in a wide field range. So this is an effort at making something that's just practical, that you can start to use and start to play with, but not necessarily pushing the absolute highest possible sensitivity. And the control unit looks like this. It's a black box with a USB port and a serial port and a little light that tells you what it's doing. And inside, the keys of making this thing work are the laser, in particular the pulse laser. So this is one of the pulse lasers we use and built. And what's amazing about this is that although we get watts of power, we're only delivering continuously milliamps of current, right? Because we're just concentrating all that current into short pulses. So it has this extraordinary wall plug efficiency because when the laser's on, it's all the way on. And when it's off, it's completely off. So that's just a wonderful thing. And you really, it's like a VCSEL. You treat it like a VCSEL in sort of power and thermally and everything like that. And I hope also cost. And the other thing that's really critical is the frequency counter, which is integrated into our control unit. And so we've made a frequency counter which has extraordinary common mode rejection. This is with fake signals here. If everything's very clean, the common mode rejection is really as large as you want, in some sense, because it's a frequency measurement. So, this is showing that this frequency counter has the performance that you need at this sort of 10 femtotesla level for ideal signals. So, of course, you take this particular sensor out into the world, and all you see is 60 hertz or 50 hertz. And it can be huge in the office, right? It can be hundreds of nanotesla, peak to peak. And so this is useless, right? So obviously the thing you need to do is to form a gradiometer. And so this little section of the talk describes a project that I'm working on with Micromolis and a team at SRI. So Princeton, SRI, and Twinleaf have been working very hard in the last year on improving this sensor. And I think it's tremendously exciting. The idea is to put two sensors, of course, right next to each other and share lasers. And so many things are common mode, and let's see what it looks like. So it looks like this. This is, of course, a really early prototype. And there's lots of empty space in this box, but we put it all in a box. Critically, the first cell is only about 1.5 centimeters. The center is only 1.5 centimeters in the front, and the baseline of the gradiometer is about 3 centimeters. And of course, those numbers will improve. We'll get it closer to the front. So we're going to put this in front of our heart and measure our heart. This is simple enough. And so here we are outside. This is actually an earlier version of the sensor in this box. And you can see what we have here is this cable to a little pile of control electronics, and it's all running off of USB off of this laptop here, and we're all staring. I'm not wearing my glasses, so I'm sort of squinting at my heartbeat, and this is Dave Newby. I did have to take my glasses off, but other than that, I didn't have to do anything, and I just walk up to it and I see my heart. Oh, wait, actually, I don't see my heart, I see this. And this is, of course, more 60 hertz. Which is, it's likely to be real gradient 60 hertz. So there's a lot of gradient noise, and we can filter it out. So if we apply notch filters at 25, 60, and 120, and a bandpass filter, and just to sort of put us in context, we're right next to these gigantic power lines here. And so 400 nanotesla, we have the most magnetic possible office here, and so we walked over here to do our test. So you actually here and here. So it's about 30 nanotesla peak to peak. This is still an awful lot of background noise, but nonetheless we're able to make reasonable measurements. And so this is my heartbeat. And so what's nice is that you can see these sharp signals and also this thing. And I'm not an expert in these things, and sometimes you can also resolve the smaller whatever it is. And I'm not an expert, I'm so sorry. But this is, a demonstration that, just walk up to the thing and you can take these measurements without any fuss at all. In fact, you can even hold the magnetometer in your hand and just in the ambient environment and make these measurements. And I think that that's a real, achievement. And then I went for a run and ran as fast as I could, and I came back and I just walked right up to it and I measured a faster heartbeat, and that's good, I guess. No, this it works. It's great. The heart works, and this works. And so if we just took the FFT of that data, this is totally unoptimized, unideal. The orientation of things was not, carefully, designated. So here we're seeing huge 60 hertz, and there's some other peaks here. This I can't quite tell. One of these is 25 hertz, which is due to our trains, which are very close by. And anyway, so the noise floor here, this is the filtered signal that we did to see actually you see the heart signal. Unfiltered, it's right around 29 femtotesla here. So that's, it's very, very promising. It works over a range of fields, and critically, it works around Earth's field, which is, for us, it's around here. And the noise is actually a little bit better, so it gets under 10 femtotesla per centimeter per root hertz. Our baseline is 3 centimeters, so multiply by 3 to sort of get the field resolution. So we dip down, and this is back in a shield, so these are under totally ideal conditions, no 60 hertz to speak of, and it shows you that it can work fairly well. So we went to a slightly quieter location, or tried to anyway, and here's Amtrak over here at 25 hertz. And here's power lines over here, so we're sort of in the middle, but still around a whole bunch of civilization. And we took some more heartbeat. This is a smaller signal. This particular person was a little further away, but you can actually really resolve both of these features in some cases. And obviously you can see them quite well if you averaged. So just a couple picotesla. And so if you look at the noise here, it's really promising. So in the magnetometer, we have 60 hertz, 120 20 hertz, and this 25 hertz, which is Amtrak. And environmental noise here, this is 10 picotesla, so here's 10 picotesla here. And of course, we have to have those two magnetometers subtract that noise as well as possible. And so at higher frequencies, it's actually doing fairly well here in this environment. So this is 13 femtotesla per centimeter per root hertz, which is about 40 femtotesla per root hertz. And if you sort of infer what the magnetometer would be, it would be square root of 2 less than that. Not that that's very useful. This stuff here is because we have a person here. I think these are sort of human sources. One thing that I start to see is that the noise is mirrored in the gradient. And so we see a common mode rejection of about 1,000 here. And obviously there's no fundamental reason that should be. Our frequency counter can do much better than that. And there's still it's not entirely non-magnetic. So it could be that there's still some tiny amount of magnetic material in there, and it's converting a uniform noise into a gradient noise. And so you see this noise spectrum kind of mirrored in the gradient. So obviously, one next step is to totally demagnetize the thing, and that's obvious. And maybe this will get much, much better. And this is critical, of course, for biomagnetic measurements, going from getting rid of these peaks, getting it right down to this level. We waited just a moment, and here's like a slightly quieter moment. But even so, this factor of 1,000 or so common mode rejection still is putting in some noise here. But it looks like this is something that we can eliminate just with technical improvements. So in summary, we have this beautiful new sensor. It works outside. It has this incredible gradient sensitivity. With the caveat that we're doing this in a fairly quiet environment, 10 nanotesla peak to peak. It also works at 30 nanotesla peak to peak. You can see the heartbeat just fine. And it also works in 100 nanotesla or 200 nanotesla peak to peak. But there you start to get significant gradient noise that will degrade the sensor. Bandwidth of the magnetometer is, the sample rate is 300 hertz. The bandwidth is flat. So, the way forward, of course, is to make this more practical, more small, and completely remove magnetic materials and really push on the sensitivity. Just a sort of a note of how these things actually work in practice. All of our sensors have a serial port that comes out. It's really handy. It's a differential serial port, but it's a standard. And you can convert that to USB and plug it into your computer. And when you first plug it in, you get a line of numbers, which is just nanotesla of magnetic field. And there's also a binary format. You can go to our GitHub page and download all these things to help you work with them. And we love this. This is a Python tool. You can driverless just connect the magnetometer. You import Twinleaf device, and off you go. You can start making measurements. It's super awesome, and it's super handy for doing really nice automation and data collection. We have LabVIEW tools and so on like that. This is part of this awesome ecosystem of Twinleaf sensors. They all now synchronize. And this is a huge development for us as we've put so much effort into how do we really time and frequency synchronize all our sensors. And so this is a board that we've designed to do that. And you can plug in actually all these heterogeneous sensors, and they all agree on time and frequency, even the ones that don't need frequency. So microsam, microsurf, the pulse magnetometer, and so on, even the current supplies. And you can get huge multi-channel arrays. Now we've got many different synchronization units. Some of them have GPS synchronization, and you can daisy chain them to form huge arrays, and the data is collected via Ethernet. So that's where we're going, and we're preparing and we're laying the foundation in all our control electronics to really have arrays of sensors. So summary is that we've built this beautiful pulse gradiometer. It has these fantastic performance specifications, and we saw MCG. There's some limitations, and the thing that I kind of want to point out at the very end here is that we just got used to zeroing our fields, right? And we're used to getting these fancy shielded rooms. Now, for this type of sensor, we have to zero our gradients, and we don't have to. And it's very similar in some ways. It's best at 0 nanotesla per centimeter. And yes, if you have a few nanotesla per centimeter, it's fine. And 40 nanoteslas per centimeter is too much in some sense. So that's what I have to leave you with. Thank you.